All right, so I want to move on to chapter 6 directly, which starts the abstract ring theory in earnest. We want to talk about ideals, something called the quotient ring construction, which is going to be sort of the central thing, and the first isomorphism theorem. And then we want to go back to chapter 5 as another detailed example. But I want to start with something called the kernel of a ring homomorphism. And before you start this, it would be a great idea to go back and read through the section on rings, subrings, and ring homomorphisms. So the general definitions, just review them before we start. But I'll remind you the definition of a ring homomorphism. Let's start there. So recall a function f from R to S, where R and S are rings, from a ring R to a ring S, is called a ring homomorphism. We'll just abbreviate it like this. If f of A plus B is f of A plus f of B, and f of AB is f of A times f of B, and this is for all AB in R. So a ring has addition and multiplication, and these are functions between rings that preserve both these operations. Given such a ring homomorphism, we define kernel of F. So that's the new word. To be this thing. It's denoted by the symbol ker of F, and it's the set of all A in R such that f of A is 0. And by 0 I mean the 0 of S, of course, because F goes from R to S. There is a similar notion in linear algebra you might have seen. It's called the null space of a matrix, or the null space of a linear map, or the kernel of a linear map sometimes, or a linear transformation. It's all the vectors that go to the 0 vector when you apply this linear transformation, or when you multiply by the corresponding matrix. And you know there that this null space plays an important role in understanding the nature of the matrix or the linear transformation. And the same is going to be true here. So there's some sort of motivation behind looking at this object. And it actually plays sort of the same role that it played in linear algebra. So this is our first lemma. Looking at this kernel can tell you when a homomorphism is one-to-one. So a homomorphism, and here on, by homomorphism I always mean ring homomorphism, because that's the only kind of homomorphism we are going to talk about, unless I say otherwise at least. A homomorphism F from R to S is injective if and only if the kernel is just the 0 element. This you may recognize this from linear algebra. The similar result was true. Of course, a homomorphism, ring homomorphism, takes 0 to 0. We checked that when we introduced homomorphism. Look back. So 0 of R is in the kernel. And now if F is injective, then different things go to different things. Because 0 goes to 0, nothing else can go to 0. So in that case, the only thing that goes to 0 is the 0 element. So then the kernel is just 0. So if F is injective, then kernel is 0, this is an exercise. Verify. Let's just put it. Verify that if F is injective, then kernel is 0. The main point is the other implication, that if the kernel is 0, then it's injective. So it's a way to check that our homomorphism is injective. So suppose, let's do that implication. So we are assuming the kernel is 0. So suppose the kernel is 0, if A, B in, so let's say I want to show that the function is 1 to 1, right? I want to show that my F is 1 to 1. So how do I show it's 1 to 1? I take two things. So let A be in R such that they go to the same place under F. F of A equals F of B. I want to show that A is B. But if F of A is F of B, then F of A minus B is F of A minus F of B, because F is a homomorphism after all, and these two things are equal, F of A and F of B, so this is 0. 0 of S. So A minus B is an element which, when you apply F to it, you get 0, so this is in the kernel. That's the definition of the kernel. But the kernel is just 0. That's what we are assuming. So A minus B is 0. So A equals B. And that shows that your function is injective. Okay? So this little thing tells you that the kernel is a useful thing to look at. Now you can go back to the list of ring homomorphisms that we gave after we defined a homomorphism and calculate the kernels of those homomorphisms. That would be a good exercise. I've written it out in the notes, which ones would be good to look at. Let's keep this first one short. We'll continue